drastic difference in X-ray diffraction pattern. So the dried ribbon here, you could actually see a strong C stacking peak corresponding to the C stacking. But the previous one, if you dry this up, both will have a similar density, but then you don't see an obvious stacking. Okay, so this was really the turning point for us, because with this we realized that now we have a material system, a bulk material system, where you have chemically identical building block, but the only difference here is really the way they stack, the way they assemble. So we took inspiration from the freshman level of material science class. Actually, this was one of the class I was teaching. If you think about the way microstructure of metal, so other than chemical composition, if you think about the microstructures, we can start with a single crystalline material. That's the perfect long-range arrangement of the units. If you mess up the arrangement, say you create grain boundaries, you generate a polycrystalline material, but which is actually now harder. Okay, it's actually a stronger material because now the grain boundaries help to retard dislocation motion. And if you keep increasing the level or decreasing the level of ordering, ultimately you could actually generate a glassy state. This is basically referring to this fascinating group of material called a bulk metallic glass. Now, we would think while we were teaching and learning that, at the same time, we were inspired to think that can we actually achieve similar or a analogous structure, just like that, a set of analogous structures. So for 2D materials, you can certainly have a single crystalline structure. For example, if you look at a single grain of HOPG or high quality graphite or MOS2 crystal, you will get a single crystalline grain. But if you look at a bulk solid, okay, it is not going to be a single crystalline solid. And it is usually made by densification and pyrolysis. So what you have is that you're going to have these different crystalline domains, but they are going to be jammed up together. And in between, there's going to be some disordered connectors or much weaker connectors. Now, a glassy state would mean that you do not have these long-range order in C stacking, but yet you still have a densely stacked sheets. And this will require the sheets to crumple up, okay, and to entangle with each other. So with that in mind, we designed this experiment to study the effect of the microstructure of the sheets. Microstructure refers to the geometry of the sheets and relative entanglement. So here we can start with a three-dimensional graphene oxide foam. If you just uniaxially compress it, you will generate a pellet, and this pellet is certainly lamellar in microstructure. So this is our control experiment. This is normally how you would generate a dense solid made of graphene oxide sheets, or actually any powder materials, right? You compress a pellet out of it. So a control experiment is that we first wet this with a moisturizer, with a handheld beauty spray, okay? And then we let it dry in air, and this creates a much more isotropic compression force field. So in the end, you're generating a pellet. Now we do have to slightly adjust the shape using a very gentle compression, just so that the shape matches. But the pellet still is largely disordered, okay, because it lacks the long-range stacking here. And this can be seen in X-ray diffraction. Now the two pellets have similar density. So then this is meaningful. I mean, if you have a very low density foam, then you could have no C stacking, but that's not a fair comparison. So basically now we have two pellets made of identical units in terms of chemical composition, and they also have a similar volumetric packing density. But now if you look at the hardness, this is just one of the easiest property to probe when you have the solid. So with the lamellar pellet right here, you can clearly see that the density, the hardness along the two different directions is different. So intuitively, if you have a book, right, if I take a book right here, if you have a book and start to indent along the normal direction, and that will be the hardest direction. And if you look indent on the edge, then that would be the softest direction, because now when you indent, the sheets can readily peel open and slide. And hardness is a measure of the resistance of material against permanent plastic deformation. So the isotropic behavior of the lamellar solid is perfectly understandable because they have these isotropic microstructure. Now, when we move to the glassy graphene oxide solid, then as expected, the hardness is now much more isotropic. If you measure along the side and measure along the top, it's about the same. But what's most striking is that the hardness now is actually harder than the vertical direction of the lamellar solid. Okay, so that was a little bit puzzling in the beginning, but then we realized that it's also perfectly reasonable because in the lamellar solid, we are not really having a single crystalline lamellar solid. It is a polycrystalline solid, so that means when we indent this, we are going to push these stacks. We're going to push these nicely stacked domains apart because they're connected by weaker domains. Now, in the glassy solid, because the units are now heavily entangled with each other, so collectively they have a much stronger resistance to slippage of the sheets, and this gives them the higher hardness. So we're pretty excited by this because this is a pretty neat example to show that you now with the bulk solid, the property of that can clearly be influenced by how the units are connected, are assembled together. This is actually becomes a classical nano assembly problem. Okay, now this is graphene oxide, and we really like to push this to at least reduce graphene oxide to the more conductive, more graphitic version. So next we tried painstakingly trying to reduce this glassy graphene oxide. So to make a long story short, we eventually got it through a combination of slow heating and thermal compression process. So here I'm just showing you that we are stepping up the game. We're now comparing what we obtained later on here. This is essentially the reduced graphene oxide monolith. We are calling this like temporary as a graphenic glass because it's also disordered, and the sheets are now RGO, which is chemically modified graphene. Now we're stepping up the game because we're not just comparing this to the lamellar solid, we're now comparing this to isotropic graphite, and these are among the hardest graphite engineering materials out there, and these are made by carbonizing and densifying these graphite precursors or graphite powders at elevated temperature. And typically, these need to be heated up above 2000 degrees C, and they need to be constantly held under very high pressure. But with the graphenic glass here, we are just reducing this at about, first at about 200 and then just at about 700 or 800 degrees Celsius. Because we were really limited by the hot press that's available to us. That's really the only hot press we could find at Northwestern back then. So if you look at the Raman spectrum of the two materials, I'm going to spare the details, but basically if you're familiar with the Raman spectroscopy of carbon materials, this tells you that you have much higher quality graphite domains, okay? And the left side is RGO, is much worse, okay? A lot more defective. And now if you look at the X-ray diffraction, the isotropic graphite, because it's made of these graphite crystallites, it has a strong stacking peak here. It's a high quality domain, right? High quality stacked sheets domain. And the graphenic glass side has a very little diffraction intensity at the same position, and their densities are comparable. But now if you look at the hardness, we observe the same thing. So this disordered arrangement turned out to have even higher hardness than isotropic graphite. Okay, and this the reason again to summarize this in the glassy graphene solid, we have much weaker unit because the sheets are porous, defective RGO instead of much more perfect, more perfect graphene sheets in the graphite product. But because of the extensive entanglement, this hinders the slippage between the weaker units. So collectively, they actually produce a higher hardness. But for the isotropic graphite, which is again is among the hardest engineering material made of graphite out there, they do have much harder grains because these are essentially individual graphite, but they don't have very strong grain boundary interaction, the grain boundaries can slip if you indent it. So again, this echoes the what we saw with the graphene oxide glassy solid, and we're pretty happy that we were able to benchmark this against a commercial product. Okay, so we're still moving this slowly, mainly trying to improve the dough making process and try to improve the reduction, the conversion process. So this has been a significant delay by the pandemic because my students have shifted gear almost completely to address some of the more pressing issues in the pandemic. Almost my entire group is now studying respiratory droplet modification. But with the reopening of the campus, they are now gradually returning to their previous project. So I hope to show you more later on. I think I still have some time. Okay, this is to wrap up the idea here that other than just generating new structures, I think this really illustrates the opportunity that two-dimensional materials can contribute in generating new engineering bulk-size material. If you think about how people, say, tune a microstructure with metal, is typically through a plastic deformation. You can tune the grain sizes. There are ideas like a powder metallurgy. You take powders and densify them, but then you don't control the size and the interaction of the grains. There are a lot of nano building blocks out there, nanoparticles, nanowires, but when you try to densify them, you're going to encounter two fundamental challenges. One is the scalability in material and scalability in properties. The second one is really the stability of those nanostructures, because when you densify these and anneal this, you might lose a lot of those nanostructures. But 2D materials have a unique advantage because it is fundamentally scalable, and it actually fundamentally is a lot more stable against sintering. So you will have a lot of opportunities to generate exciting new microstructures and new materials. Okay. So let's see, how am I doing in time? I think I still have a few minutes. Okay, so let me switch gear to talk about a second type of dough, which is carbon nanotube dough. And this is really motivated by a discovery about solvent nanotube interaction and also the state of the art of the material. So nanotube in a powder form has been mass produced. The best way to look at this is to see where you can buy it from. So in US, you can buy it from eBay. In Amazon, they even offer prime shipping. You can get it the next day. And if you go to Alibaba, you can see some really large scale samples that you can add. Like, for example, the minimum order is 1 kilogram for this type of multi-wall nanotubes. So why haven't we seen this being used very, very widely? Well, the challenge again is it's not easy to use them. They aggregate, okay? So this is a schematic illustration just to see what you get in the starting powder. You're gonna get clumps. Now, when you disperse them in solvent, if you don't have a good dispersion that can disentangle these tubes, you're just gonna get a dispersion of these aggregates. But if you can truly disentangle them, then you will be able to generate, again, that evolution in 4 different states that I showed earlier, like the bread flour states, right? You can start with a dilute soup, dispersion, a thick paste, a freestanding gel, and eventually maybe a moldable dough. Now, solution processing of carbon nanotubes has always been relying on surface functionalization. You do some covalent chemistry to modify the surface, or you have to search dispersing agent like some surfactants or some polymers. But the problem of both approaches is that it either contaminates a nanotube or it damages the surface. So after processing, you either get degraded surface or you just have to figure out a way to remove those surfactants if you don't want them to be in there. So ideally, if you have a solvent or solvent system that can just dissolve them or disperse them, then that will solve all the problems. So to make it, again, a long story short, the net take-home message is that we discovered that a Cresol solvent, especially m-cresol here, is a fantastic solvent for dispersing almost all types of nanotubes. And these are very common chemicals. They have been mass produced for a variety of reasons. And if, here's a fun part, right? At least in this pandemic, Lysol product has been extremely popular. But Lysol is actually named after m-cresol because that was the active ingredient in the first generation of disinfectant, Lysol disinfectant. But of course now they replaced it with something else. But the name, the sol in the name is actually Cresol. Okay. It is also a naturally occurring chemical, and you can find this in many plants or in a petroleum refinery process. So here's just a quick show of the results that you can disperse powders of heavily aggregated multi-wall single nanotubes in m-cresol. And you can do this by the typical lab technique, like you can do probe sonication, or if you want to scale this up, you can actually use a shear mixing that actually also seems to disperse them pretty well. Okay, now if you benchmark this with the some of the most commonly used solvent out there, especially NMP and methylfluoridine. NMP is the, I guess, is almost like the standard solvent people use now to process multi-wall nanotubes for battery making, right? You can, if you want to use multi-wall nanotubes as battery additive, you make an NMP paste, you blend it with other particles. But if you look at the dispersion property, this clearly can disperse a lot more nanotubes than the other common solvents. And if you look into, we employed a number of spectroscopy techniques to confirm that. The reason that Cresol dispersed nanotubes so well is that, well, Cresols, or a mixture of the Cresol monomers, the solvent, is a liquid, it's a solvent at room temperature. That's very important. And secondly, it has a charge transfer interaction with carbon nanotubes. And this is most visible in proton NMR. You can see a clear peak shift here. And this interaction is non-destructible, so it's non-destructive. So after processing, you have several ways to remove Cresol molecules, and you see that the Cresols are not polymerized or reacted. And also, if you use single nanotube as a Raman marker, we don't see the structure of nanotubes being altered. So it does appear to be a non-destructive solvent that can be used to process it. So then we basically try the same route. We start with the powder. You can generate a high quality dispersion. If you use just a grinding, simple or careful grinding, you can generate a paste, a freestanding gel, eventually also generate a Play-Doh. And the transition between these states are marked by a threshold-like increase in electrical conductivity from dispersion to a paste. From paste to gel, you have a sudden increase in viscosity, and from gel to dough, you have a sudden increase in compressive stiffness, indicating that now you are generating something, you're generating a matter of states towards solid. And you can have a lot of fun with this. Again, as I mentioned earlier, that if you have a breakthrough in processing, this can help a lot of people because people have many different needs in how they want to use carbon nanotubes. For dilute dispersion, you could do, we demonstrate here, Langmuir project sampler, you can get really nice monolayer here. And this, of course, connects to transparent conductors. I shall say that this particular slide was actually obtained by a former KAIST visiting student, Segi Byung, and I believe he's now working in a national lab in Korea. And then the paste is suitable for screen printing. This is the typical technique that people employ to make battery electrodes. We did this just to illustrate that it is compatible with battery making. And it is important to have a cohesive paste. If you try to force a paste made of NMP, as we mentioned earlier, if they don't disperse well, the paste is pretty much a dispersion of high concentration of aggregates. And when you try to do blade coating, it's not going to give you a continuous film. Okay, and the gel turns out it is a freestanding and it's even printable. You can actually demonstrate some rudimentary 3D printing structures. And finally, the dough is really fascinating. Again, in this case, the dough is a high-loading nanotube, high-loading carbon nanotube system in Cresol, and the mass loading of the solvent and the nanotubes is close to 1-to-1. So in a way, you can view this as if you have a carbon nanotube solid with Cresol molecules as a plasticizer. So if you have Cresol in it, it's moldable. It's very soft and moldable. If you vaporize the cresol off, it's hardened, become a hard solid. If you put cresol back, it gets softened again. It's fully reversible. Okay, and the difference between a dough and a gel is that a gel can stain a surface if you roll it. Okay. Now, again, just to illustrate that you really need to have a good solvent for this, here's a quick video just to show you if you force a dough out of a poor solvent like NMP or other solvents, you can have a dough-like material, but it's not manipulatable. Once you try to manipulate, it will fracture because you're not having a uniform and cohesive microstructure. But this kind of dough is very manipulatable because, again, you have now a continuity in microstructures. Okay, so there are a lot of things you can do with that, but I'd like to go back to, again, processing. This dough here is a very high concentration of carbon nanotubes in m-cresol or in cresols. Essentially, this is a high loading of charge transfer complex between nanotubes and cresol. And if you dilute this in common industrial solvent, and we found out that you can actually have a clean cut, okay? Some solvents are compatible with this charge transfer complex. So for example, for solvent 1 to 5 here. So this actually means that if you use solvent 1 to 5, you can actually now use very little cresol. Okay, here, the photo here shows that the minimum cresol is 10 volume percent, but in practice, we can push this down to even 1%. So that means you can use cresol molecules as a minority solvent and then make carbon nanotubes processable in common industrial solvent, okay? And we were able to, again, using a hydrogen NMR, we were able to actually figure out a selection rule. And we now know mechanistically what kind of solvent is compatible with this charge transfer complex. And if you look at this list, hexene, toluene, and chloroform, these are all very common industrial solvents. And if you look at other solvents like acetone and ethanol, and including methanol, these are not compatible, so nanotubes will crush out. And I will show you that the compatible solvent is very handy for high throughput solution processing. And here we're demonstrating this with a single nanotubes. Again, the starting tubes are heavily aggregated. This scale bar is 100 microns. So after you disperse this in m-cresol and hexene, this is a quick spin-coated film. You can see the tubes are now nicely dispersed, and you can actually just load it in a commercial spray gun, spray gun, yes. You can buy this from Amazon, okay? Now you can do a very quick spray coating on many different substrates, and you can get a conformal coating. Now, for those incompatible solvent or bad solvent, and turns out that they are also useful because they are incompatible. That means they're going to break the charge transfer complex. And this becomes a very quick way to remove any residual cresol. So here we show that initially we got a cresol containing film, a wet film. You can clearly see the cresol signals. If you wash it with a compatible solvent, which means that it doesn't break the charge transfer complex. And after washing, you still have cresol. But now if you bring in an incompatible solvent, it will cleave cresol away readily. Just by a simple dipping, rinsing, you can just remove cresol. So to conclude this, now if you think about the dough, for manufacturing, it becomes a high loading of this charge transfer complex between carbon nanotubes and cresol. And finally, this connects carbon nanotubes with common industrial solvent. You can use compatible solvent for high throughput processing, and then you can use incompatible solvent for rapid removal of any residual cresols if you don't want them. So now notice that this whole process doesn't involve any surface functionalization or any surfactant-like additives. It's basically a solvent cocktail. So we hope this will provide people a solution in their pursuit of nanotube applications and accelerate their own discoveries. Okay, so I should stop right here. The first graphene oxide part was led by a former graduate student, Dr. Zhening Ye. She is finishing up a postdoc at Stanford and on her way to National Tsinghua University in Taiwan to be an assistant professor. And Haiyu has been instrumental following her and assisting her in that work. And then the nanotube work was led by a former student, Kevin Cho, who just graduated a few months ago. She just started at National Sun Yat-sen University, also in Taiwan. And she was helped out by Zhulong, a new postdoc, and Cheer, a former MS student. And then also I should mention that this is a Lars, a visiting student from Germany, and Hong Park from Hanyang University. By the way, Hong Park is the scientific grandson of Professor Samuel King. Okay, he's also doing extremely well with higher in pursuing new directions of the graphenic glass. Okay, so thank you very much. I will be happy to answer any questions you may have.
Okay, thank you for your great talk, and I especially like your Mickey Mouse doll.
Okay.
By the way, so it's time for the Q&A session. Okay. The first question is, thank you for your great talk, Professor Huang. You may have already mentioned it, but could you comment on how to control the fraction of lamellar to glassy graphene oxide upon desiccation?
Okay. Okay. So now we were trying to get the same volumetric density. So we basically that means we're trying to get the same density and also as high density as possible. So that means the lamellar one here is really our reference, right? I guess we don't really control that because we compress it as much as we can. Now, the degree of lamellar arrangement in the glassy one, that can be controlled by how you dry it. So for example, okay, here's one. If the starting dough is more isotropic in shape, because the geometry sets the boundary of the wetted gel, and that physical surface is where evaporation will start. If you're starting a geometry is more isotropic, then you are generating more isotropic capillary compression field. If you have an elongated rod, then when you dry it up, you're not going to get a glassy structure. You're going to get a thin wire that again has preferential. Well, that's actually not a very good example. If I flipped it, if you have a large disc, okay, and dry it up, then you're going to have a preferential stacking. So I guess you can control the degree of lamellar arrangement by controlling the boundary or the geometry of the hydrated foam, hydrated structure before drying. Okay, I hope that makes sense.
Okay, thank you. The second question, thank you for a nice talk. Could you comment on the quality of graphene CNT after handling the dough for a large number of times or after extended storage?
Okay, so for the graphene oxide dough, I guess I don't know what do you mean by quality, but I guess it refers to are they still as manipulatable and as moldable, right? So for storage, there's no problem as long as you don't dry it, or as long as you don't heat it, okay? Because heating triggers an irreversible change of graphene oxide. So even if you dry it up, then you can still put water back. That's not an issue. But if you dry it up or contaminate, accidentally introduce contamination like metal ions, and that will mess up the redispersion property. That will also change the sliding behavior. Now for the carbon nanotube one, because Cresol doesn't vaporize very easily, the boiling point is about 200 degrees Celsius. So that one you could actually keep it easily for a very for extended period of time. Now after manipulation, so for the graphene oxide one, if you, for example, roll it to force the lamellar arrangement, then it gets harder because then it will no longer be as moldable in the ribbon state. To return it to the moldable ribbon state, you will have to knit it. You have to fold the ribbon up and knit it. We use a mechanical shaker to help to knit it. Knitting helps to randomize, or again, to increase the level, to increase the disorder in sheet stacking. So that would be one way to do it.
Okay, thank you. For the last question, thank you for the great talk, Professor Huang. What about to mix 2D and 1D nanomaterial in terms of desiccation and other bulk properties?
Yes, that's a brilliant question. That's a brilliant suggestion. We did try to add single wall nanotubes into this graphene oxide dough, and indeed, you can think about like the microstructure here. If I borrow this structure, if these are two-dimensional sheets, and if you introduce some single nanotubes, which by the way, you can do that by just sonicating graphene oxide and nanotube powders together, because graphene oxide can indeed disperse them. But in this case, it would be difficult to generate just individual tubes. You might get bundles of tubes, but that might be okay for the microstructure. So if you do that, the nanotubes are basically stitching up these soft sheets. So we do have a much enhanced cohesivity and also much enhanced hardness. Okay, it gets a little bit harder to manipulate because it gets harder. Okay, but I do agree that if we look at mechanical properties and especially the densification behavior, I think that will give us perhaps even harder graphitic monolith later on. Okay.
Okay, thank you. We just got one more question. Thank
Okay.
you for your nice talk. In your talk, m-cresol and CNT interact well with each other. How about pristine graphene or fluorine and m-cresol?
That's also a brilliant question. So how about graphite and fluorines, right? So now, for some strange reason, they don't seem to be dispersed as well as carbon nanotubes. They do get dispersed at a much higher concentration than other solvents, okay? But they don't reach as high concentration as the carbon nanotubes. My suspicion is that the curvature changes the local electronic structure, at least alter a little bit for at least for single nanotubes. So that might indicate that there is some selectivity in chirality here. The other reason for why graphite is harder to disperse, because the stacking between graphene sheets, I believe, is much stronger than the bundling, than the interaction between nanotubes in a bundle. So that's probably why nanotubes seem to be dispersed a lot more easily than graphite. Now, let me clarify that for graphite, when you disperse it, you generate a few layer of fine graphite platelets. I'm sure we have a lot of single layers, but for us, it's not concentrated enough. But my student told me that it's actually more concentrated in something like NMP. But we were really hoping to get almost like a pure single or few layer monolith or gel, but we haven't been able to do that. But we do get like a fine platelets dispersion with the platelets of like tens of nanometers, like 50 nanometers or so. So with that, if you can live with that, then you can actually generate a very high loading.
Okay, thank you for the answer. And much thanks to speaker Professor Huang again.